But we're also going to talk about R squared and outliers today. Um, Now, in most problems on the AP exam, for most AP problems, correlation R is given. So they'll tell you here's what R is. Now, how they tell you might look a little bit different, all right? So sometimes it's a little bit hidden, or it looks like they didn't but they did, or the way they've written it is very subtle and so you don't see it. However, we can also find R by using data points. In other words, the graphing calculator. Typically, they do not ask this on the actual AP exam, so I'm backing away in regards to homework assignments I'm giving on this, because of just how we need to cover the material that we need to really cover that's on the exam. The reason why is because you can enter 1 point wrong, and then it's all of a sudden everything's off. So typically they do not like you to utilize technology with data points to calculate something, because you can do just one simple, your button finger slips on a button and all the information can be incorrect. So it's something that you should know can be done. I've kind of taken off the problem from yesterday's and today's homework assignments that incorporated this, because I don't feel it's a pressing need for us at this moment. I love to go into it more, because in terms of being practical, in terms of being actually able to do it in real life and actually apply what we're learning, is utilizing technology to do what we're about to do right now. But you can use it using a graphing calculator. So you do this by, of course, entering the data, and typically we put it in L1 and L2, all right? And then we got to make sure, and this is something that it's in there is so yeah, so correlation is a measure of strength for the linear relationship. As such, we need to find the linear relationship in order to find R. So you got to kind of ignore what's going to be showing onto here, because right now we're not going to use it. But the R is based on those values. So before we do that, and this is very important, we need to turn diagnostics on, and this is for TI calculators. And like I said, this is more practical usage in the real life, rather than I'm not going to probably ask you this on your homework. I'm probably not going to ask you this on your exams, but it's something that in real life, and you should be able to understand how to use your technology, is something that's helpful. So to turn diagnostics on, there's a button next on top of the 0 button that says catalog. And so what you do is you hit the second or shift button, and then you go to catalog. And inside here, you can just actually hit the button that says yours should be, if you're just using a regular calculator, it should go under all of the other ones. But it's you type in diagnostics and there'll be one that says diagnostics on. Now, this calculator, this one has it. I don't know why. I find it is one of the dumbest things. TI graphing calculators default to diagnostics off. It's not going to be important for what we're going to find right now, but it will be important for what we find later on. But it should always be on. If you're using a calculator app such as mine right here, it's already on. I know, sounds kind of weird. So to do this, you go to Stat. After you've inputted the data, and you go all the way down. And is it the same number on this one as well? Oh, the numbers are off. And you go and you select line reg A plus B X. This is the typical one we use. Now, if you notice on number 3 in the calculator, or the first one, you notice that if you go in a calculator, there's a line reg AX plus B, and then there's a line reg A plus BX. There is no difference between the two. They both do the exact same thing. This is more so chapter 8 material that we'll get into, but here's the premise and statistics. In your traditional algebra class, you use the equation y equals mx plus b, right? That's your slope-intercept form. In most all other mathematics, we don't use mx plus b. We would do what is similar to, we always like to put the y-intercept first, so we would do b plus mx. A quick justification in terms of the reasoning why we do it this way is that sometimes we want to be, we typically use this equation to approximate what's happening. That's what you do, like you make a line to approximate. But sometimes we might want to be more specific. So instead of just going to just mx, we can, instead of fitting a line, we can actually fit a parabola, ax squared plus bx plus c. We can actually fit a trinomial, ax cubed plus bx squared plus cx plus d. We can do all those. We can keep tacking them on. And it's easier to do it as a plus bx because when I want to add something more, I just add it to the next one. So a is still a is always the y-intercept, b is always the slope, and then when I add in a c, that c refers to the x squared, and a d would be, the numbers would keep going on and slapping on over there. Now, that's also typically why we use subscripts, because when you get to do too many letters, the other letters start meaning other things in mathematics. So we use like a sub 0 plus a sub 1 x. I'm not going to go into it too much in terms of our course and try to let you know, but I want you to point out that just they're the same thing. The only difference is that if you use the first one, what you find for A will turn out to be your B for the other one. Because A in the first, whatever number's attached to the X, that's your slope. All right, so if you pick number 3, A would represent the slope and B would represent the y-intercept. But if you select number 7, which is the one we traditionally use in our course, A represents the y-intercept and B represents the slope. And I put my data into L1 and L2, and I go to calculate. Now, some important information came up here, okay? It tells me what R is. So it calculates, it does all the calculations for me. So the calculator, when you do this, will calculate R, okay? It'll do the calculation such that it finds the value of R, and R is equal to the summation. So what it really does is for every single problem, it finds the z-score for x, this is the summation right here, times the z-score of y, and it multiplies them together, and it divides them by n minus 1. Now, you never need to use formula. Calculator will do it. So the calculator will do this formula. So there is a formula for calculating R. It's the z-score. So for every single coordinate has a z-score. It has a z-score for x, how far it is away from the mean of x's, and a z-score for y, how far away that point is in terms of how many standard deviations it is away from the mean of y or the mean of x. Once you do that, you multiply those two numbers together and you go on to the next point. You find the two z-scores for x and y, it multiplies those, and then you go on to the next one. You find all of them for every single point, you add them all together, and you divide by how many points there were, minus 1. Don't worry, you never have to do it in this course. But you need to understand that there is a calculation there. The calculator calculates that for us. All right, so it does that for us, and in the previous problem, on height versus shoe size, it says that R is equal to 0.88. Now, how would we define that relationship? How would we define the strength? Strong, yeah, strong, and it's right on the verge of being very strong. So it's strong to very strong. It's right on the edge, right there. While we have some good cutoffs, and we say anything right below 0.9 is strong. We need to realize as statisticians that there's not some magical thing that happens that if you take 1 inch forward, all of a sudden your entire world changes. So we need to understand that. It's the same thing about the outliers, right? So I would say strong. However, like you learned in last night's homework, you better take a look at the scatter plot, right? We can't, R tells us nothing unless we know that there's a linear relationship. So that's very important. There must be a linear relationship. If there's not a linear relationship, so this is a strong if linear with no outliers. So it can indicate, sorry, I wanted to say indicates strong if linear with no outliers. Now, inside the calculator, it also shows you another calculation, R squared. So it says R squared is 0.78. I'm going to talk about this very shortly, but 0.78. All right, so this is something I'm going to talk about, and it has a very important meaning. And big R squared is literally the value of R squared. All right, and it has some very important meaning interpretation that we need to make sure we have in statistics. But I want you to note that value, that if I square 0.88, I get 0.78. Now, with our technology, we can actually graph these, all right? We can actually do this just like the histogram stuff. It's not necessarily something that's going to be really pressing for the AP exam, so I'm not spending as much time on it. If we had the full year and we had time where we can be together and do some actual data collections and applications, we would. But we can go to Shift Y equals stat plot, and we can go into the stat plot, turn it on, and if I look at that very first graph, that little dots, those dots are for a scatter plot. So if I select that, it's a scatter plot. So this tells me I'm going to graph a scatter plot where the X list is L1, which is where I put my X values, and my Y values are in L2. And if I were to graph this, I can hit zoom fit, which is in this case number 6. Oops, I'm going to go Y. Let me delete all that calculus stuff that I have on there. Zoom stat, that's what I meant to say, 5. Here is my scatter plot. So if I can look at the scatter plot, and I can change the settings on the scatter plot so that it might look a little bit better. Second Y equals. I can make it solid dots, and let's make these, let's make it blue. So there's my scatter plot. Would you define this as linear, a linear relationship? Yes or no? Is this a linear relationship?
No.
Yes. I would classify it as a linear relationship. Look at the points.
I can see the linear.
Yeah. So if you look at the points are following a line. Okay. Now, something that you can also do is that when you did that line reg stat calc, and this is typically something also that we do when we did that stat calc with that line reg, you can actually go down to where it says store regression equation, and this is a pretty cool feature. You can actually tell the calculator to put the equation in and graph it for you. And so to do this, I have to hit the vars button, vars, functions, and then usually you have to hit yvars if you're on a normal calculator, and then you hit y1. Now, what this does is that when I graph it, it'll actually, oops, I forgot to actually run it. That would have been nice. Stat calc 7 vars y vars function y1 calculate. When it does that, it actually puts the equation into y equals. So if I go to y equals, it actually puts the numbers right into there. So it graphs it for me. Now I can kind of look at this. Do these points seem to follow the line? And the answer is yeah, it seems to follow pretty good along that line. It doesn't seem to have any curve to it. So I would say, yeah, the relationship is linear. I would define the description of the form for the relationship to be linear. However, I would also indicate that there seems to be two outliers, right? My last year's class, we had somebody that was relatively short and had a very small shoe size. And we had somebody that was very tall and had a very big shoe size. So those two people were potential outliers. You can see that in the far left point here, or the far right point there. That person it was an outlier. He was very tall and had a very large shoe size, but he still followed along the pattern. And this individual, she was very short and she had a very short shoe size as well. So, but overall, they both still followed along the pattern. So there are outliers, and outliers can affect the correlation. So we got to be careful. So that although R is 0.88, R is probably not as strong as that value indicates because there are outliers. Okay. Now, R is calculated on z-scores. Okay, and the formula R equals the summation of zx times zy over n minus 1. I could have written this as R equals the summation of zy times zx over n minus 1. And if I multiply zx times zy or zy times zx, I get the same thing. 5 times 2 is 2 times 5. There are certain implications for this. Okay, so what are the implications? You need to know what the implications of the formula. You don't need to know the formula, but you need to know the implications of the formula. Okay, the first implication of this is that R is unitless. Or R has no units because it is based on z-scores. And z-scores have no units. So first things first, because Z has no units, changing units does nothing to R. So it doesn't, if I measured you in inches and I go, well, you know what, let me measure in feet, R is still the same. So it doesn't matter if I measure you in feet, if I measure time in seconds, inches, seconds, minutes, hours. If I change the units for either of the variables, I measure you in degrees Fahrenheit versus degrees Celsius, the correlation value that gets calculated will be the same. That's a very important piece. Does everybody understand that? You'll get that question tonight. Second implication of this being based on z-scores. Sorry. So R has no units. So changing the units does not change it. Well, that's the implication. Sorry, that is the implication. So if you slapped units onto R and you said R is, this is R, and you slapped on units like meters per second or meters, that's wrong because R does not have units. Also, if you change the value of the units, what happens of the variables? What happens to R? Nothing. The other implication of the formula is that Zx times Zy is equal to Zy times Zx. And what this means in terms of its implication is that switching the x and y variables does nothing to R. So in other words, it doesn't matter if I have, if this is height and this is shoe size, or if I measure this as shoe size here and height here, R is equal to R. The same, you do not change R. Okay? R does not change. And the reason behind this is based on this formula right here. It's based on this formula. All right? Z-scores, which means that there's no units. So it doesn't matter what units I'm measuring the variable in, because the mean will be, if the variable numbers change, then the mean and standard deviations will reflect to those changes as well. Okay? Now, when I say changing units, that can happen. So changing units, and this is also some tricky you'll see in your homework, is if I make a transformation to all points. So if I'm measuring you in feet and then or inches and I change it to feet, that means we would take every number and we would divide it by 12. Every number gets divided by 12. And since every number got divided by 12, we're just changing units. It's a transformation to all points, which means that the R value would stay the same. Alrighty. Any questions? So you have a lot of homework, or not a lot of questions, but you'll see those type of questions pop up. Outliers. On correlation. Okay. There are two types of outliers. There's outliers that are in the path, like this data had, and there are outliers out of the path. Okay, so you can see from this data here that for the most part, the cluster of data points is right here. And those 2 points would be outliers. Outliers in the path of data will increase the value slash strength number of R, but it doesn't actually do that. So it'll make R appear stronger. And now this is also true. I want to point out that this is also true that if my points go down and I have an outlier down here, this point R, this point increases R. However, removal of outlier in path weakens R. Now, R is only a good measure. Once again, R is only an accurate measure of strength if the relationship is linear and there are no outliers. So if there is an outlier, we have to pay attention to that and we got to say, well, here's the value of R. However, it's probably a little bit higher than it really is because this outlier is making the value look bigger. Outliers out of path of data decrease the value strength number of R. So it's the opposite. So if I had some data points and I had this outlier over here, this point here is going to decrease the value of R. So if without that point, R is, if I only had these points down here, I might say R is like 0.95. But because there's this point over here, this kind of point over here is going, oh, don't forget me. So when I calculate my R, I might get an R that's like 0.6. Now, if you looked at this relationship, the data point, this is a very strong relationship. However, if you calculate R with the data points, you might get an R of 0.6, which is moderately strong. So you can't base the strength solely on the value of R. You got to look at the data if you have the scatter plot. Now, if you know there's no outliers, or no, at least no extreme outliers, and you know that the relationship is linear because they tell you, then you can take the premise of the value of R and determine strength from that. And once again, opposite, right? If we removal of outlier out of path will increase R. All right, now let's finish this lesson. I told you about this value R. If I square R, we call this R squared with a capital letter. And typically the reason for R squared is that R squared is typically written as a percentage. So i.e., in my previous example, I found that R was equal to 0.88, and then if I squared that number, I got R equals 0.78? 0.78. So we would say that R squared is what? How would we write R squared? How do we change that to a percentage, people? You've done this since elementary school. Are you there? Hello.
Is I don't use the square root.
No,
So I have no idea, mister.
just elementary. You didn't even do square roots. Before you even did square roots, you did this. What is this number as a percentage? It is written.
78%.
It's written as a percentage. Yeah, so 78%. Okay, so when we define r squared, we write it as a percentage. So we wouldn't say r squared is 0.78. We would say r squared is 78%. Now, what is r squared? R squared, and this is an important information. This is mostly for most of you it would be memorization. It is the percent of variability in the y variable that is explained by the relationship. And if we're doing linear relationship, it's linear, but it might not. You can also do r squareds for any other type of relationships of the linear relationship to x. And this is a very interesting concept here, and it's a game changer in terms of a lot of stuff. So yesterday I talked to you about the idea of attendance. More attendance, there's a correlation between high attendance and high grades. There's a positive correlation, more importantly. So typically, students with higher attendance have a higher grade. However, it's not correlation. It doesn't mean that if you have higher attendance, it does not mean you will get higher grades. I've seen students who have very poor attendance do all their homework, ace their quizzes, get A's. I've seen students who come every day and do nothing and just sit there and you're like, why are you even here? And they get F's. So there is a correlation, but there's not a causation. And the reason why is because R while it's strong, it's not 100% for R squared. The correlation isn't 1. It isn't perfectly linear. In other words, you do more homework, or you show up to school and automatically your grade goes up. There's other reasons. There's other parts that explain it. All right? And so R tells you, okay, so if my grade's going to change, my grade can change. How much of my grade change can be explained by my attendance changing? Okay. So for example, your grade goes up by 2%. Okay, 2 points. You went from an 81 to an 83. Now, but it might have gone up to 83, it might have gone down. So there was some change, there was some variability, there was some change in your grade. Okay. And the question comes up, okay, so how much of that was because of your attendance? What percent? How can you explain to me how much of that grade change of the not it's and you've got to be careful here, and this is really really tricky. It's not of your grade change; it's the variability in your grade change. So how much your grades can vary. How much of that is explained by your attendance? Well, it's r squared. Once we find the correlation, it's r squared. So for an example, in the problem that we had up here, based on what I did, where I got r squared was 78%, this tells me that from last year's class, 78% of the variability in shoe sizes is explained by the linear relationship to height. Now, this is a sentence that you'll be asked to do, and this is very important for us. So 78%, shoe sizes, height. You only actually have to plug in 3 things. You have to plug in the context of the problem, and you have to plug in the variability percentage. Everything else is a memorization statement. Blank percent of the variability in X variable is explained by the linear relation to blank, whatever the Y variable was. That's it. All right. So that does have some important things. And I see that it's 9:50. Just give me 30 more seconds. So when I said R is 0.9, if I said if R is greater than 0.9, this is the same thing as R being greater than 81%, or R squared being greater than 81%. So we define this as very strong. And the reason that this is very strong is because we're saying 81% of the variability. That's a lot. If I told you 81% of the reason why your grades change is explained by because of your attendance, that's a big explanation. So you would want to say, oh, wow, I need to focus on my attendance if that means, but you got to realize it doesn't mean causation. It doesn't mean that if you fix it, if you improve it, your grade does not automatically change. Same thing, r equals zero point 0.7 is r squared equals 49%, which is about 50%. R equals zero point 0.5 gives you r squared equals 25%, and r equals 0.3 is r squared equals 9%, which is about 10%. And so 10%, if I only give you anything less than 10%, you're like, I don't even care. It's less than 10% of the reason. I don't care. 25%, now we're talking. Okay, now we're talking. You give me a quarter of the reason, we're talking. And if I tell you at least half of the reason, now we have a strong relationship. So there's the statement. There's the class. Sorry for keeping you over. You have a great weekend.